Welcome back to ECE 442, 542. I had to cheat to see which class I was actually in. Here are the announcements which you've been seeing if you're in class, and I don't know if it was clear to you, but I changed the description on lecture 1.2 saying there's additional notes at the end, and I talked a little bit I wrote down a little bit more information concerning questions that were asked after class relative to that S, capital S, which was really just the sum of that finite sum expression. How did I arrive at that answer? And that's appended to last time's notes. If you are an online student, then you need to determine how you will take the exams, either through Examity or through a proctor. If you're on main campus, don't worry about either of these two. You don't have to find a proctor. I am your proctor for the exams, but please, if you're an online student, that's due on the 10th of February. The passport assignment was due yesterday. If you still have not completed that, I don't think the Dropbox has been locked and secured down. You can still submit if you would, and I would appreciate you doing that so that I can maybe put a name and a face together and maybe a meal, or at least a food item, right, with the name. Homework 1 is due in a week, and that you will submit into the assignment folder designated for homework number 1. You should look at that. If you're doing MATLAB, I want you to provide enough MATLAB material so that if you looked at that description in 6 months, meaning you probably need more than just an M file. I'm not going to execute everybody's M file to check your work. Include the results of executing those M file statements. You could do a diary command to record your session and then say echo on and then type your M file name, and it will now record or remember your MATLAB instruction and the displays that occurred. And if you have graphs or figures, you could then copy those and paste those into a Word document together with that echoed set of diary commands in MATLAB. That would then be a way to document what you did for the MATLAB problems, hopefully in enough detail that in 6 months you could say, oh, yes, I know what I did. If you just have the MATLAB code, then you have to remember what each of those commands mean. And what were the results? Well, the results are maybe the important thing. Maybe you're trying to figure out how does this system evolve in time. If you just have the MATLAB commands, maybe you can't or obtain an intuitive feel for what's going on based on just those commands. Reading assignment, and in particular for today's material. So if you are listening to this online, I guess you can pause and go study these sections. Now, after the fact, if you haven't pre-looked at these note-taking templates, now you know that we're dealing with sections 4 in chapters 1 and 2. Those are dealing with block diagrams. We'll talk about that today. We're also talking about solutions to homogeneous and non-homogeneous difference equations, linear difference equations, both for a first order and in chapter 2 is a second order. And we also will talk a little about, maybe we probably won't get there today, is the relationship between the S variable that you're familiar with, Laplace transform S, that's a complex number, and the Z variable, which is a complex number for discrete time systems. Today what we want to do is look at the solutions for forced and non-forced difference equations. Non-forced are homogeneous. Forced, meaning you're pushing it, you're exciting it, is non-homogeneous. We'll look at those, and we'll also talk about settling time for discrete time systems. Here is a first order response, and this is maybe now as you are pulling money out of an account, and maybe that account balance is disappearing at a 5% rate. That's now going down exponentially. When do you get, at what time step, which I'm calling n sub s, at what time step do you get to 1% of where you started? That's your 1% settling time. We'll show how to derive that n sub s value. And that actually is needed on homework number 1, problem number 4. Problem 4 actually uses the same difference equation, but it uses parts A and B under 2 different scenarios. Part number A, you have a non-zero input and a 0 initial condition. Part B is the reverse. You don't have a forcing function. Your input U is nothing, and you have an initial condition. And you now need to answer those questions for those 2 different initial conditions. And in part B, you will be looking to find, what is my settling time? What is this capital N sub s? And there is a picture of that, and this 1% settling time means when do you first enter into and not exit that 1% tube, where the 1% tube is determined by your initial value of that variable. If you're thinking about something that's oscillating back and forth, you might go through that 1% tube a lot, but the settling time means you go into the tube and never leave the tube. Is that making sense? And it's cleaner or clearer when you just have a first order exponential decay, and then it's not changing signs, it's not bouncing back and forth, but you could have a oscillatory behavior, and you want to know, when do I get into the 1% tube and never leave? That would be its 1% settling time. We'll also talk about block diagrams for difference equations or discrete time systems, and we could draw 2 different block diagrams. One in the time domain, where our dynamic block is really a delay. It's a 1-unit delay block. Or we could do it in the frequency domain. Now we're dealing with this complex variable z, and now that delay block in the frequency domain is this operator z to the minus 1. And we could have 2 different block diagram descriptions for the same system. One in the time domain, one in the frequency domain. The frequency domain, we can then, with some algebra, find the transfer function between the input and the output, or transfer functions. Like in one of the homework problems, you're looking from different inputs to maybe different outputs, so you could have multiple transfer functions for the same system. And for an all delay block diagram, if we simply label the outputs of our delay blocks as state variables, bang, we immediately have a state space representation in the discrete time setting. And getting maybe ahead of ourselves, but I want you to be thinking about, what if I had a continuous time system and I actually wanted to sample it? How fast do I sample that? What's my sampling frequency, f sub s? Or what's the time interval? What's the sample period? What's the time interval between samples? That's capital T. The sampling frequency, f sub s, and the time interval between those samples are reciprocally related. That's f sub s is equal to 1 over t, 1 over capital T. So you'll hear somebody say, well, what's the sampling rate? And they may give you the frequency, they may give you the sample period, but you could find one or the other based on given one piece of information. We will be looking then at how do we pick the sampling frequency, f sub s or omega sub s, given a continuous time system, the idea would be to sample, actually now this is, why did I do this? The rule of thumb, I got 2 pi on the brain. I guess I was hungry thinking of pies, but the sampling frequency is now 30 times omega sub c. So if you're working from your template, you'll need to correct that. The sampling frequency is now you want to sample 30 times the highest frequency in your continuous time system. This will make more sense as we get there. I'm just sort of giving you an outline of where we will be going eventually. And to begin today, what I want to do is talk about homogeneous linear difference equations. And it's maybe easier or cleaner to have this discussion with a particular example. Here is one. And based on what we talked about last time, what's the order of this difference equation? Pardon? Is it third order? Second order? Do I have a 1 or a 4? What is it? So now we would solve for the highest index. In this case, it would be x sub n. And then we look and see, okay, all of the terms on the right, how many more of those or previous indices do we see? We see an n minus 1. That's 1 before. We see an n minus 2. That's 2 before. Oh, it's actually a second order. We have 3 terms, 3 indices, but the 1, x sub n, is only written in terms of 2 previous. So this would be a second order difference equation. And this particular example has nothing driving it. It's only the dynamic behavior of the system. We need to somehow initiate the state of that difference equation by kicking it or setting the initial conditions. By kicking it, I'm really initializing the state. I'm not inputting. So maybe I shouldn't have said kick it. Let me just give you the initial conditions and then see how it evolves in time. There's nothing forcing that, and that's this hard 0 on the right. There's no u of n. This is the input, is u of n, and I'm going to overload u of n. U of n is going to mean all sorts of things. Generically, u of n is the input sequence, which could be anything. But I may get sloppy and say, oh, you know what? U of n is actually my unit step here. So that would be a 1 at time 0, a 1 at time 1, a 1 at time 2. It's just 1 for all values of n. So I will overload u of n, and hopefully it will be clear from context how u of n is being used. Generically, it's just a input sequence of numbers that I'm using as the input to the system, how I'm hitting it or forcing it. Here I'm not forcing it. I'm simply providing initial conditions which will now allow me to evolve in time based on how I began or initialized that system of equations. Or in this case, this second order linear difference equation. I want to find a closed form solution for this second order difference equation with the appropriate given initial conditions. I'm given the difference equation, I'm given initial conditions. My goal, what I want to find, is a closed form solution or an analytical solution. I want to see x of n is equal to some expression that I can just plug in and I can tell you what x is at that time instant, at that sample period. That's the goal. Typically, I'll call that a closed form solution. Here's the process. We first, just like you've done for solving differential equations, you assume a solution structure or form. For difference equation, that structure is a constant a times a z raised to the power n. And this is actually a exponential structure, and the sub h on x is meaning this is the homogeneous structure solution for that second order difference equation. I want to find capital A, which is a constant, and this complex variable z, and depending on the order of my difference equation, I'm going to have multiple constants A and multiple values of z. Second order, I'm looking for probably I am looking for two constants, an a sub 1 and an a sub 2, and two frequencies or complex values of z, z sub 1 and z sub 2. And I'll add those together to obtain my homogeneous solution. That's the goal. If you're playing along in your head as far as what you did for differential equations, maybe this looks familiar to you. Maybe you assumed a k e to the st for a solution structure. You plugged that into your differential equation and found the k's and the s's that satisfied that differential equation or system of differential equations. That you can compare with this structure. Oh, I have a linear difference equation. It's going to have an a z to the n structure. Now I need to find my a's and my z's. That means we substitute this structure into our given or original difference equation. And our difference equation that I gave you was x of n plus 3x of n minus 1 plus 2x of n minus 2 is equal to 0. I said I'm assuming x of n is a z to the n. What's x at time n minus 1? And I'm going to scale that by 3. If this is x of n, how do I change that to make it x of n minus 1? It's maybe too easy, right? You just plug in where you had n, you plugged in n, now you have an n minus 1, you plug in n minus 1. This is now a z to the n minus 1. Likewise, for the last term, you now say, oh, I need to plug in or substitute in x of n minus 2. And I need to now find a or a's and z's that satisfy this equation. And we want a non-trivial solution. We don't want a z to the n to be identically 0. And if that's the case, then we can factor out a common factor from this expression, the common factor being a z to the n minus 2. And to be a non-trivial solution, this is not going to be equal to 0, which means we'll be able to just divide that out. And what we want to equal 0 is going to be in the square brackets. If I've now factored a z to the n minus 2 out of a z to the n, what's left over for the first term? Or what, when multiplied by z to the n minus 2, yields z to the n? Hopefully you see that that's z squared. We do the same for the rest of this equation. We have a 3. A pulls out, and now we need something times z to the n minus 2 to equal z to the n minus 1. And I'll just make that more explicit. I'll say that's z to the 1. And then we have, what else do we have next? Now we just have 2 times z to the 0, but that's 1, so why put that in there? And that's equal to 0. We've now actually found what we want. We found our characteristic polynomial. And that should sound familiar to you from a differential equation class. Now we're in difference equation class. That's our characteristic polynomial. If we set that characteristic polynomial equal to 0, then we end up with what we call our characteristic equation. We now want to find or use the solution to that characteristic equation to find the values of z that we want. And this is a second order equation. When we have a second order or quadratic, we would expect two values that would satisfy that. You could plug this into the quadratic formula and obtain the factors, the z values, that solve that, or you could simply factor that if it looks like it's factorable, which it is, and now you have the solutions. We've now solved the characteristic equation by factoring in this case. And we see that if we set z equal to -1, that left-hand side would equal 0. That's a solution. If we let z equal to -2, that likewise will cause the left side to equal 0. That's another solution. Our solutions then to the characteristic equation give us two values, which is what we were anticipating, and those two values we actually will say are our natural or our characteristic modes of the system. Those are the natural modes of this second order difference equation. The modes are now what we use to produce our homogeneous solution structure. We use each one of those modes and we simply add it up with different unknown coefficients for the a's. For example, we now have an a1 times one of the modes minus 1 to the n. There's our structure that we had assumed, but we also have a second one. And now this is our, in fact, our closed form solution. And what do we want to do with that? Or what do we now need to find the a's. The a's that actually, and how do we find the a's? Now that we didn't have a non-homogeneous, we didn't have an external input forcing this, we can now find those unknown coefficients, a1 and a2. We'll find those to satisfy our initial conditions. We now find a1 and a2 from the initial conditions. We were told a of 0. A of 0 we were told was 1. Well, that must be what this closed form solution evaluates to when n is equal to 0. That's a1 minus 1 to the 0 plus a2 minus 2 to the 0. Knowing what we know about exponents of 0, what's in the parentheses of those terms is just 1. In this case, we now know that this initial condition gives us one of our equations. We better get two, since we have two unknowns from our two initial conditions. We now know how A1 and A2 are related. One equation. We know 1 is equal to A1 plus A2. We also were given what the value of x was at minus 1, and we were told that that was 0. We now know that A1 minus 1 to the minus 1, this is when n is equal to minus 1, plus A sub 2 minus 2 to the minus 1. Or 0 is equal to, and what's the inverse of minus 1? Minus 1. And what's the inverse of 2? Minus 2 in this case is the minus 1/2. Now we have a second equation that involves A1 and A2, these unknown coefficients. You could solve this however you want. Let's just use the second one and say, oh, A1 is now minus 1/2 A2. And we can now use that in our previous relationship, which said that 1 was equal to A1 plus A2. We know what A1 is. That's minus 1/2 A2 plus A2, or that's 1/2 A2. A2 is now 2, and A1 is half that size negated. It's minus 1/2 A2. We now know our closed form solution specifically is A1, which was minus 1 times minus 1 to the n, plus A sub 2, which is 2, minus 2 to the n, and that's true for n greater than or equal to 0. How does that system behave? Can you tell me, now that I've given you this closed form solution? How will this move now that we've initialized that system to have a value of 1 at 0 and nothing in an earlier time step, or at n equal to minus 1? This is how it behaves. Well, let's just get a feel for that by subbing in some values of n. As we increase that n, we'll see how is this behaving, this system, to those initial conditions. Is it going to collapse? What's going to happen? Well, we know how it began a no, not even very long ago. X of minus 1, it was 0, and x of 0, it was 1. What's x of 1? Well, we can just plug in n equal to 1 into that expression to evaluate it. We now know that that's minus 1 times minus 1 to the 1 plus 2 times minus 2 to the 1. What's the first term? Minus 1 times minus 1, that was 1. So we turned 180 degrees and we turned another 180 degrees. We're back where we started. That's one way of thinking about two negatives making a positive. The other term? Is minus 4. So we were at 1, now we've gone to minus 3 in one time step. What is x at time 2? We do the same calculation, just plugging in n equal to 2. The first term is now minus 1 times 1. And the next one is 8. Now we flopped up to 7. Oh man, what's x of 3? First term, 1. Second term, minus 16. Oh. Now what have we done? We've turned around and gotten bigger. What are we doing? Is this system bounded? No, it's going unbounded, and it's changing sign at every time step. This is what we would call an unstable system. And thinking ahead, what were your values of z? They were, the characteristic modes were minus 1 and minus 2. To know how this is going to behave naturally or characteristically, you sort of compare their magnitudes or their values relative to the unit circle. Are these values related to the unit circle? Are they both inside the unit circle? Is one outside? All it takes is one mode outside the unit circle to make this go unbounded. You had something at minus 2. If you just had that one, it would be terrible. Not terrible, but it would be going unbounded, right? And it would be changing sign at every step because it's minus 2 to the n. What would let's say we didn't have that minus 2 and we just had the minus 1. What would that be? That's what some books like to say is marginally stable. Is your magnitude growing? No. To an initial condition, it's just the magnitude would be staying the same. It would just be changing sign at each time step. You would be, let's say your initial condition was 7. You would be 7, minus 7, 7, minus 7. You might get dizzy, but you wouldn't go unbounded. Because you're right on the stability boundary. You're right on that value of z equal to 1. I would say stay away from the boundary. Stay away from values z equal to 1 because I could find a way to excite that system in order to make you have an unbounded response. We'll get there in a little bit later. But I could now excite that system in such a way that I could start to go unbounded with time. So the bottom line here is if you want to know, is this difference equation stable or unstable, what do? You find the solutions of your characteristic equation and you compare those to the unit circle. You're now examining the roots of the characteristic equation relative to the unit circle. And now that unit circle, you're saying unit circle, units, that's on this complex z-plane. We're going to be talking about various planes. It's not the green plane grass, or this is now the z-plane compared to the s-plane, etc. It's a complex plane in the, we'll say the z-plane, where this is in fact the complex z-plane. And if we wanted to sketch it, which this now gets a little bit challenging for me to draw a unit circle, but I hope you get the idea. That's supposed to be a radius of 1, There's 1. Here's minus 1. This point is j, and this point is minus j. This is the complex z plane, where this is the real part of z, and there's the imaginary part of z. And that negative goes down. Didn't want to shortchange it, but my circle got a little larger than my axis. But that's your z-plane. You want, if your roots of the characteristic polynomial, if we labeled those as x's, you would like all of your x's x's live in text. You want your x's to live inside the unit circle. I don't know where that came from, but maybe you'll remember the z-plane. Okay? All your x's live where? Inside in Texas, yeah. Inside the unit circle, which means that you're stable. You must be outside the unit. Anyway, I hope you get the idea. You want your roots of the characteristic equation to be inside the unit circle. They could be over here in the left half plane. They could be in the right half plane. They could be on the imaginary axis. What are you measuring or looking for those x's? You find the magnitude of that x, and you want the magnitude to be less than 1. If that's the case, you have a stable system. If you had a pole here, not a good thing in terms of a bounded response. Questions on that? That's now our homogeneous difference equation and some discussion on bounded and unbounded response. Let's now look at a non-homogeneous. Question?
Yeah, for the homogeneous system, is there another form instead of the az to the n for the homogeneous one?
So the question was, are we going to be okay if we, here I'm paraphrasing, are we going to be okay if we always use a z to the n to find the values of z? And the answer is yes. We're dealing with linear difference equations. Now they are going to possess that structure, and we'll find our characteristic modes or the natural modes of our system by assuming a structure of a z to the n, plug that in everywhere we see an x of n, and solve for the z's. If we had a third order difference equation, how many z's are you looking for? 3. If you had a first order, you'd be just looking for 1 z. Did that answer your question? So just stick with that structure for finding your z's. Now let's talk about a non-homogeneous linear difference equation. To make this discussion, again, we're going to pick an example, and I'm actually going to pick the same homogeneous equation so that the only thing different is the forcing term. Meaning, my example is now going to be, again, a second order difference equation, x of n plus 3x of n minus 1 plus 2x of n minus 2. But now I'm going to force that with something that's exciting that difference equation, and that's going to be 1/2 to the n. And I want this to be defined for n greater than or equal to 0. And so the question was, is this the u? This is now And here's where I'm going to overload things. This could be the u of n. Here I'm going to be more explicit and say that's my forcing function, u sub f of n. So my forcing function is now u sub f of n, which is 1/2 to the n, and here's where the overloading could be. I could maybe write that as u of n, which means I just want this to be on for values of n that cause the argument of u to be non-negative. For n equal to 0, n equal 1, n equal 2. Here, u of n is the unit step. Or I might say, which I did above, u sub f of n is alternatively written 1/2 to the n for n greater than or equal to 0. Instead of saying comma n greater than or equal to 0, I might get cute and say times u of n. U of n is just really like a switch. That's the unit step. It has a value of 1 as long as n is 0, 1, 2, non-negative. If little n was minus 2, then u sub f of minus 2 is nothing. It's not on, is it? It's 0. U sub f of minus 2. What's u sub f of minus 1? 0. Because little u of minus 1 has a negative argument, and that's the unit step. Here I'm saying that u of n, I think I know why this microphone was bad. Do you hear it kind of popping? Is that bothering you a little? Okay, just filter that out. It'll just bother me. How's that? Somebody left me a note and said, this is what's bad. And I turned it on and it seemed fine until I started moving around. So I have to stay bounded where? Inside the unit circle. Oh, never mind. I have to stay focused. I heard a joke, but I can't repeat it. Not here. Where was I? Staying inside the unit circle. I'm trying to stay bounded. Oh, this is what I was trying to say. U of n is 1 for n greater than or equal to 0, and it's 0 for n less than 0. That u of n is the unit step. We clear on how I might confuse you? I don't mean to, but I'm hoping by context you know what is implied when I give you a u of n. Is he using this like the unit step, or does he mean this is just a general input? If it's general, then that's like the u sub f of n. It needs to be some sequence of time. We want to now find a solution for this forced linear difference equation. And the steps are similar to how you've solved differential equations. You find the natural solution, which we've already done, which is another reason why it's helpful for me to use the same structure for the second order difference. And then I find the particular solution. I add them up, but then I wait until I've found the particular and before I find the coefficients A1 and A2 in the combined solution or total solution. Let me try to write those steps down. I now want to look at the homogeneous solution, which is the zero input solution. And if you were paying attention, what is that for this example? What is, let me now distinguish that as, oh boy, that's supposed to be an H, and what's inside the argument is supposed to not have quite the neck on it, the giraffe. It's a small neck, that's an N. We see the distinction? X sub H of N. Those are two different letters. The H stands for homogeneous. What's the structure of the homogeneous solution? Now you can't yet go so far as to plug in the specific values for A1 and A2. You have to wait until you found the particular solution before you evaluate for A1 and A2. But you do know the structure. You do know the Z's. Those you can plug in. We now say, oh, this is A1 minus 1 to the n plus A sub 2 minus 2 to the n. And this is from before. The caution, which I will write in red, not much of a caution there, is there? But in red, just as a warning, I'll say don't solve for A1 and A sub 2 until we find the structure of the complete solution. And the structure of our complete solution will include the particular solution. We have to add the particular and the homogeneous to obtain the complete solution. What's the particular solution? We found the homogeneous solution. What's the particular solution for this difference equation? Particular? What? What's particular about this equation? What's forcing this? What's exciting this? What's the particular signal that's driving this difference equation? 1/2 to the n. That's the particular structure. This linear, so if you had a linear system and you excited it with a sinusoid, what are you going to see in that linear circuit? That same sinusoid, that same structure. That's, if you hit it with an exponent, you would see that exponent in your solution. That's what we're doing here. We want to know what's the particular structure that we will see because we're forcing this linear circuit with a 1/2 to the n. What's going to have that same structure? It's going to be a 1/2 to the n. We just have to figure out what's its weight. We now know the particular solution structure, which I will subscript p, x sub p of n, is now a sub 3 1/2 to the n. This is the same structure as the forcing function. Are you already ahead of me in your questions? What if our z's, when we solved the homogeneous, what if we ended up with a z that was equal to 1/2? Darn. And we're forcing it with a 1/2. Then we actually make the particular solution independent of that homogeneous structure. And to make it independent, we have to introduce some weights, an n, like we did a t in the differential equations. We maybe had a t e to the minus 6t, or a t squared, depending on how many e to the minus 6t's we had. Here, if we had a solution to our characteristic equation that had a 1/2 to the n, oh, wait a minute, now we're forcing it at that same mode. We have to create the opportunity in our solution for it to have an independent piece. an aside, hopefully I'm not confusing you, but as an aside, if suppose, and this is not what we have here, because here we have z1 equal to minus 1 and another z equal to minus 2. So this is not I want to say particular. This is not the situation I'm showing you or illustrating with this present example. I'm doing an aside. Suppose the homogeneous solution ended up with a z equal to 1/2. We would have then had our x sub h of n as, let me just give it some, well, maybe I'll give it a b, which is not quite as good as an a. A b (1/2 to the n). Okay? We would have to select then for our particular solution, and suppose that our forcing function then we would need to say our particular n is going to be a c 1/2 to the n, but that's the same as the x sub h, so we have to put an n in there. Maybe I need to make a little bit more. Cn. That's the aside. That's the independence of our b 1/2 to the n. Now it's Cn times 1/2 to the n. We've put an n in the coefficient that weights that particular solution. That's the aside. Let's, pardon, n is being multiplied by c. So however you want to write it, Cn, notice that's Cn and not, never mind. I was looking for news at the Cn, I don't know, CNN? Sorry. I was waiting for the news to come on. Gosh. Can we get back to the class, please? What are we doing? We now need to find a sub 3. Once we found a sub 3, we can add that to our homogeneous structure, then use the initial conditions to find a1 and a2. That's where we're headed. Let's now find a sub 3. And to find a sub 3, we're simply going to plug that structure for our particular solution into the non-homogeneous equation. Meaning we had a sub 3 1/2 to the n. That was x of n. Then we had 3 x of n minus 1. But now our x of n minus 1 is actually x sub p of n minus 1, which we said was a sub 3 1/2 to the n minus 1. Plus 2 x sub p of n minus 2, which is a sub 3 1/2 to the n minus 2. We're plugging it into the non-homogeneous equation, which was forced, which was 1/2 to the n. That difference equation needs to be true or valid for all n. We need to find the value for a sub 3 based on that fact. This is true for all n. Let's just use one that's convenient. Maybe n equals 0 is convenient. Let's just use that. So with n equal to 0, we now have a sub 3, 1/2 to the 0 is 1, plus 3a sub 3, 1/2 to the minus 1, plugging in n equals 0, plus 2 a sub 3, 1/2 to the 0 minus 2, or minus 2, equaling 1/2 to the 0, which is 1. Everything is determined or known except for a sub 3 now. I now have an a sub 3, and I'll factor that out. One of those. I have 1/2 to the minus 1, that's just 2, times 3, which gives me 6, plus 1/2 to the minus 2, or that's 4 times 2, or 8. Those were all factored out of a sub 3 equaling 1. Or I now have 15a sub 3 is equal to 1. Now I know what a sub 3 is. And that allows me to write down explicitly what my particular solution is. My particular solution was a sub 3, which was 1 over 15, 1/2 to the n. My complete solution is the sum of my homogeneous and particular. My complete solution, maybe I should say, is x sub h plus x sub p. Doesn't matter, but it's just convention, I guess, to put the homogeneous plus the particular. Or x of n is now a1 minus 1 to the n plus a sub 2 minus 2 to the n plus 1 over 15, 1/2 to the n. I can now solve for a1 and a2 using the initial conditions that I've been given. I will let you do that tonight. But if we now had x of minus 1 equal to 0 and x of 0 equal to 1, we will end up with, here's the answer in the back of the book, minus 2/3 minus 1 to the n plus 24 over 15 minus 2 to the n plus 1 over 15, 1/2 to the n, and that's my expression, my explicit solution for x of n for n greater than or equal to 0. That's 24 over 15. I'm sorry, you're going to have to learn how to filter my handwriting. Hopefully that's okay. And you could have checked that. When you go home, you could say, wait a minute, I got 24, so that must have been what he had. Now, what's the behavior of x of n for large values of the time index n? Can you tell me? How is x of n going to behave? If this is now an explicit solution, can you tell me how x of n is going to behave for large n? Is it well behaved? It's still going unbounded, isn't it? Because of its natural, you're going to excite it, And boy, once you put any energy into this system, it's going crazy because it has a pole outside the unit circle. It has a mode, a natural mode of -2. It's going unbounded. How is the forcing function? Well, wait a minute though. I quit forcing it effectively because I have 1/2 to squared, that's 1/4, then 1/8, then 1/16. I'm not hitting it very hard. Didn't matter, did it? Because all you needed was to get this going. Once you've excited that mode at -2, it's going to go unbounded. Even though your forcing function is well behaved. It's exponentially decreasing. We clear on that. So this is in fact still unbounded. We didn't change the dynamic behavior or the natural characteristics of that system.
Would it still be bounded if, let's say, z was in the unit circle, and but my u of f of n was like greater than 1?
The question now is what happens. You've got two questions there. Let me parse those. You've sort of flipped it on its head, which is fine, but I'm going to do it in two parts. I think the question was, what if my z's for my characteristic equation were inside the unit circle and my excitation was going unbounded, my forcing function was going unbounded? That was your question, I think. Let me do it in two stages. What would happen if my characteristic equation had all of its z solutions inside the unit circle and my forcing function was well behaved or bounded? What would you expect? Then my output would be bounded, wouldn't it? But your question is, if my natural system was well behaved, my z's were all inside the unit circle, if I had initial conditions, they would all exponentially decay. But my forcing function, since it's, let's say, 4 to the n, it's just going to keep hitting that system harder and harder with each n, and it's going to go unbounded. So you're going to put in an unbounded input, you're going to get an unbounded output. This system, you could put in a bounded input and get an unbounded output. This would be bounded input, bounded output, unstable. This example that we just illustrated. Other questions? Yes?
Are there examples of systems like that have unbounded roots or unbounded poles?
So are there systems like that have unbounded roots? You haven't seen my bank account, have you? It's just going through the roof, I wish. Or maybe a nuclear reaction, maybe, but a lot of, what we have is a linear circuit, an RLC circuit, that's well behaved. But you can have systems that are naturally unstable. Let's go the other way. Let's say that we now do have a stable discrete time system. How do we know how long it's going to kind of be hissing at us or making noise or having a response? What's infinity? I like to kind of kid about this in terms of maybe in circuit classes I say, when is infinity not infinity? In electrical and computer engineering, it's just 5 tau in the continuous time setting. When tau is maybe 1/10 of a second, we just have to wait half a second and we're at infinity. We're at our final value. What happens in discrete time? Where's infinity? It's still bounded, can be. Let's figure that out. So this is what I was talking about before. What's the settling time? Wow. for discrete time systems. And I want all of my roots, my z's, to be inside the unit circle. So stable. Settling time for stable discrete time systems. If I have a root outside the unit, if I have a root outside the unit circle, you can't talk about settling time. It's not going to settle. It's going to go unbounded. And let's just, for something to talk about, let's consider a 1% settling time. And we can talk about this settling time concept with a very simple system, a first order system. Consider an initial condition response. We don't have to have an input. Our input could be 0, but we want our initial value of our system, or the state of our system, to be capital M at time 0, where capital M is something other than 0. Again, I said we could look at this and get the idea, understand the concept by looking at a first order system. There's a first order difference equation. Y at time n plus 1 is equal to a y of n. Why did I choose y? WHY? I don't know. It could be x. X of n plus 1 is equal to a x of n. Could have been v. V of n plus 1 is equal to a v of n. And let's just say that a, let's give it a value. 0.887. Where did that come from? Out of thin air. I just picked it. It is less than 1. It is stable. Let's now find the settling time. Which is doable because our system is stable. We could have picked it to be minus 0.887. Its magnitude would still be less than 1. It's still stable. It might be bouncing around, but it's exponentially decaying as it goes back and forth. Here, let's just look at it going in one direction. We now have, pictorially, if you're thinking about this in terms of a visual, here's y of n, and this is now y of 0. Here's y of 1. And these distances, although they don't look it, use your imagination, are the same length. There's time step 1, time step 2. That just keeps going, and we want to know, when do we get inside this 1% tube where we, for a first order, we're just coming in with a positive sign on A from one side of this. So we wouldn't need the bottom part of this tube, but this is now 1% of where we started. This is minus 1% of where we started. If it was flopping around, we would want to know, back and forth I mean, when is the first time index that it gets into the tube and stays in the tube. That's what we're after, and we want to know there's y of n sub s. We can think this through very directly. We can say y of 1 is a y of 0. Y of 2 is a y of 1. But y of 1 was just a of 0. A y of 0. So that's now y of 2 is a squared y of 0. Y of 3, I hope you can see, is now a cubed y of 0. And we just can follow that pattern. And this is true for any n. Let me just say capital N. But that's really our functional form that's going to allow us to evaluate our 1% settling time. The 1% settling time we actually want y at time n sub s to be 1% of where we started. We want it to be 0.01 y of 0. Therefore, y of n sub s, which we want to be 0.01 or less, y of 0, but we know how y of n sub s is related to y of 0. That's a n sub s y of 0. There's our relationship, and it really doesn't matter where we started. Do you see that we still have a raised to the n sub s? N sub s is some integer number. We want that to be 0.01 or smaller. And then what is that value for n sub s? We now know that for the 1% settling time, we have that condition. And we can solve that for n sub s, where n sub s is the number of time steps to settle to 1% of our initial value. And here's why we learned all the algebra that we learned, or the math that we learned. We can take the log of that. We want to solve for n sub s. What if I now take, and just to make it easy, since I'm looking at 0.01, let me use a base 10 log. I'm taking the log base 10 of both sides. But now I can use my knowledge of logarithms and exponents. The exponent now flops or moves in front of the log. And 0.01 is really 10 to the minus 2. And log base 10 of 10 to the minus 2 is minus 2. And that's equal to n sub s log base 10 of whatever a was, and I actually picked a particular a to do this example. I said a was 0.88 something, 0.887. I can now solve for n. N sub s is now equal to minus 2 over log base 10 of a, which is minus 2 over log base 10. And I'm assuming you all have the log tables memorized. That was a joke. We now have n sub s equal to 38.4. Well, we can't have a partial sample period. So it's going to take us, what, 39 sample periods before we get to inside that 1% tube. Therefore, the system transient, that's what we mean by the settling time. The system transient will take approximately 38, which we now know is going to be 39 sample periods. If I had actually given you a particular value for the sample period, you could give me the actual time for a 1% settling time. I didn't tell you what the sample period was here. Let me pick one after class and I'll just plug it in, and then you know how physically long that sample or that settling time was. We'll pick up somewhere next to this on Wednesday.